The first game we're going to take a look at is called the Power of Two. So the way you play this one is you pick up two four-sided dice. Now if you don't know what a four-sided dice looks like, you're not nearly nerdy enough, so go look it up. But they just look like little pyramids. So we're going to pick up two four-sided dice and we're going to roll them. And once you roll them, you're going to take the numbers that show up and you're going to add them together. This is very similar to what you do with six-sided dice for Monopoly or Settlers of Catan, if you're familiar with that game. So if you were to roll them and you got a 1 on one dice and a 3 on the other, you add them together for a total of 4. Now once you've done that, if your total is 2 or 4 or 8, which all happen to be powers of 2, then you win a prize. You get to double your money. So if it costs you $1 to play, you're going to win a $2 prize. So the point here is to figure out whether this game is rigged towards the player or if it's rigged towards the dealer or the person running the game. And if it is rigged towards the dealer, which all games of chance are, then how much money can the dealer expect to win from each game? And then if we were to sit and play it for a day, see how much money you'd be able to walk away with. So the first issue then is, what's the probability of all the different outcomes that could happen in this particular game? So when you're dealing with the dice and this type of dice game, so we're just adding up the faces, you have to think about what could happen on your first roll. So you could get a 1 or a 2 or a 3 or a 4. You pick up your dice, you roll the first one, it's either 1, a 2, a 3 or a 4 because it's a four-sided dice. Now, after that, you pick up the second dice and you roll it, and you could get a 1 or a 2 or a 3 or a 4. So those are your options. Now, what you're supposed to do with the faces is you're supposed to take what's on the first one and what's on the second one and you add them together. So if you had a 1 on the first dice, a 1 on the second dice, that would be a total of 2. And that's one of your prize values, so that'd be a good one to happen. If you got a 1 on the first dice and a 2 on the second, that adds up to 3. 1 and 3 adds up to 4. 1 and 4 adds up to 5. And oh, this one, that's also a prize value. So we're going to have to do this for all of the outcomes that are possible from this 2 dice game. So I'm going to finish drawing the chart here. I'm going to go into fast forward mode so that we can do this a little quicker. I'm going to start just to show you how to do the distribution for dice outcome. I'm going to start by doing a chart of all the outcomes first, and then we're going to get the expectation values. That's how much money we should budget for each prize outcome. And then we'll try and do this in a more abbreviated fashion to sort of see what information is important and which information can be discarded. So the first thing we're going to need is a chart to summarize all of this stuff. So one heading will be X. Those are the possible outcomes of this particular experiment. So if you get a 1 and a 1, you'd end up with a 2 as your total. If you got a 1 and a 2, you could end up with 3, etc. So this goes all the way up to, I believe, 8 is our highest value. So you could get a 2, a 3, a 4, 5, a 6, a 7, or an 8. Now, to our chart, we're going to add a column that is the probability of this particular outcome occurring. So that's not too hard to get once we've drawn this tree diagram here. All I have to do is find all of the 2's that show up at the ends of these branches and take it as a fraction out of the total number of branches. So if I look, the 2 only shows up here. That's the only way to do it, just to get snake eyes. 1 and 1 is 2. So that shows up 1 time. And if you count the branches, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, there are 16 of them. Now you could save yourself some time realizing that 4 branches with 4 branches on each, 4 times 4 is 16. So that will get you the number faster if you don't just want to count. If I start looking for the next result, this 3, the 3 occurs here and it occurs here. So that happens twice on the 16 branches. A 4 happens here, here, and there. That's 3 times on 16. The 5 happens here, 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 and here. That's 4 times. The 6 happens here, here, and here. That's only 3 times. The 7 occurs there and there. That's only twice. And the 8 occurs only here with a double 4. Now, you notice in this pattern that the probability is increasing until you get to the 5, and that happens to be the result dead center. After that point, it starts to decline. And if you look at the mechanics of how this works, there are more combinations of dice rolls that produce a 5. You could get a 1 on this dice and a 4 on this one, or a 4 on this one and a 1 on that one. So by the time you add these all up, this ends up being the most common result. If you were to roll 2 4-sided dice and add the result, a 5 is what's going to happen 4 out of 16 times. It's about 25%. It's exactly 25% actually. So you can see that by setting the game up this way, it is not equally likely to get a 2 as it is to get a 6. There's a cluster of results in the center that are more likely. And if you were to look at a game like Settlers of Catan, which again, if you don't know about, you're not nearly nerdy enough, so go look that one up. The idea is you roll 2 6-sided dice and add them together, and your tiles generate resources based on which numbers come up. And the numbers you want the most are 6 and 8, which happen to be the ones that straddle the center value. So there are many games that are set up this way. Monopoly uses 2 6-sided dice, and if you were to look at, well, there's sort of popular folklore that certain squares on the Monopoly board get landed on more often than others, and that is true on the first 2 or 3 times around the board. You're going to do a 6-sided tree diagram for 6-sided dice in the problem sets. And so when you're done that, you'll see that the most common value is 7. So from start, 7 squares in is the most likely place you're going to land on your first roll. 14 squares in is the most likely place you're going to land on your second roll. And then 21 squares in is the most likely place on your third roll. And so if you think about what squares those are, they do come up more often at the beginning. Once everybody's been playing for a while, the results are scrambled. So it's harder to say which ones are more likely after that point. But there is something to the mechanics of it at the beginning of the game. Anyway, what are we doing? Right. So now that I have all of the results that you can get by rolling 2 4-sided dice and adding them up. And I have the probability of those things happening. I'm going to add a third column to calculate my expectation value. Expectation. And the way I'm going to accomplish that is by taking the probability of this particular event occurring and multiplying it by the prize that I would win at the end of the day. Because really, I don't care that you got an 8. I care that I have to pay you $2. So if I were to go through here and highlight my prize columns, so I win money on a 2, on a 4, and on an 8. And so that would be multiplied by $2, by $2, by $2. So $2 times 1 out of 16. I'm going to render that as decimals so that we can talk about it in terms of cents, because I think that will be easier for us to latch onto. 1 out of 16 times $2 gives us 12.5 cents. So again, I got this number by taking $2 times 1 divided by 16 gives me 0.125. For this row, $2 times 3 out of 16, 2 times 3 divided by 16 is 37.5 cents. And this one, $2 times 1 out of 16, well, that's the same as the top row. And if you happen to roll a 3, you get nothing. So 0 times 2 out of 16 would be $0. 0 times this one, you win nothing here, you win nothing here, and you win nothing here. So what do these numbers mean? Well, it means that I'm going to have to pay this $2 to someone approximately 1 out of every 16 games. So I should take that $2 and spread it out over 16 plays so that I can budget for that prize amount. So if you take $2 and spread it out over 16 games, that ends up being 12.5 cents per game. This $2 prize shows up more frequently because the result of 4 on those dice, right? And you place it here, 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 that's it. Because it shows up more often, I have to budget more money because I'm going to have to pay this $2 prize out 3 times in every 16 games. So if I spread 3 prizes of $2, that's $6, out over 16 games, I have to budget 37.5 cents per game. This one is the same as the top one. The 8 shows up once approximately in every 16 games, so I'm going to have to budget 12.5 cents per game in order to pay that prize. Now, if I were to take those numbers that I've budgeted and add them all up, 0.375 plus 0.125, plus 0.125 gives me 0.625, which is 62.5 cents. So what this number is telling me is that I have to budget 62.5 cents per game to pay for the prizes. Well, that's okay, because if you check, I'm charging you $1 to play this. So if I have $1 come in and I only expect 62.5 cents to go out, that means that the difference gets to stay in my pocket. So $1 minus $0.625 is 37.5 cents. So if I were sitting like on a park bench somewhere and I happen to have 2 4-sided dice and I was charming and charismatic enough to attract people to me to give me loonies to roll my dice under these particular rules, then I would expect to get to keep 37.5 cents per dice roll. Now that's not cheating. This game is rigged in my favor, but not rigged in the dice are loaded kind of way, or this is a trick, or this is a trap, or I've somehow lied to you and I get to steal your money out of it. It's that the machine is engineered to take money from outside and put it into this pile. And if you know the mathematics behind it, you can analyze this type of game and see if it's rigged towards the player or rigged towards the dealer. Now, why would we do this? Why would I sit on my park bench and play this game? Well, 37.5 cents doesn't feel like it's worth it. But I want you to play this game over in your head, right? Add some circus effects to try and make it more exciting, right? You play it up, oh, he's going to roll the dice, or whatever you're saying in advance. So the time that takes, plus the time to take the dollar, plus the time to roll the dice and pay out the prize, or not pay out the prize, that takes about 10 seconds, which means you can play this game 6 times in a minute. And if there are 60 minutes in an hour, 6 times 60, that's 360 games. So if I were to take this prize, right, I'm expecting to win as the dealer, I'm going to keep this much money per game on 360 games. If I were to just take this number and multiply it by the number of games I can play in 1 hour, I end up with $135 per hour. I mean, that's lawyer rates. So by the time you have played this game for an hour, you've got $135. I expect to have $135 in my pocket. So it's a fairly effective machine at extracting funds from players and placing them in the pocket of the dealer. So to be a touch more efficient in this particular analysis, if I look at how the prize structure is worked out, it costs me $1 to play, and then I double my money on this value, or this value. So it's the same prize if you get a 2, a 4, or an 8. So instead of setting it up as all the individual outcomes, I'm going to abbreviate this to a win or a loss. And that's really all that I'm concerned about. So the probability of a win, well, the win happens here, 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 and there. What's that? 1, 2, 3, 4. It happens 5 out of every 16 games. And the losses happen in all the rest, right? So that should be, 11? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You lose 11 times out of 16. Now, if I were to make a little column in here for the prize, if you win $2. If you lose, you get nothing. So the expectation for this, which is taking the prize value and multiplying it by the probability of winning a prize, 5 out of 16 times 2 ends up being 10 out of 16 dollars. And if I type that into the calculator, 10 divided by 16, I end up with 0.625, which is good because it's what we had before. 0.625. And of course, 11/16 times 0 is $0. So altogether, the expected value, so this game has an expected payout of 0.625 per game. Now, if you were to think about playing this game, 5 out of 16, that's about a third of the time. Not quite, but close. So if you were to sit down and watch this happen, every third person in line wins the prize. So you might think that that's a pretty good game to play, right? That's a lot of prizes being paid out, which is why this ends up being as high as it is. So the trick to a good game is it has to be likely enough that you win a prize, or the prize has to be so spectacular that it encourages people to come play. Otherwise, it's not interesting. And so the best games are ones that have really big prizes that rarely come up, coupled with some smaller prizes that happen really frequently, in order to encourage people to come and play. If you think about Lotto 649, it's set up like that you win the jackpot of $10 million once out of something like 13 million plays. So it's practically impossible to win the jackpot, but the jackpot is so big that people are willing to throw away $1 or $2 in order to take the chance that maybe they do win it, because people do win the lottery every once in a while. The thing that keeps you coming back, though, is that if you get at least 3 matches, you get a free ticket. So your original dollar propagates, and you get to keep playing, and it feels like a win, right? Like, ooh, I got something for this. Well, you didn't. You got your money back. That's the best you got. But it feels like a win, and so that makes people want to keep playing. And so you add a few prizes in between, right? $5 here, $1,000 there, and you've got yourself a machine that moves money from the players to the person dealing it, which in this case is the government, and then they use that money to build hospitals and schools and stuff. So smart idea. But basically that's how games are set up. So we're going to do a few more. Some are based on cards, and then we're going to go through a thing called the stochastic process, where as you travel down the tree, the probabilities of each outcome change based on what's happened before. So we're going to analyze this game a few different ways. Some that are tipped towards the player, some towards the dealer. So the basic idea of Chase the Face is you draw 3 cards, and if you get no face cards, you get nothing. If you get 1 face card, you get your money back, so you win $1. If you get 2 face cards, you get $2, and if you get 3 face cards, you win 3. So it's a pretty simple game. The first way we're going to play this is inside the deck. So in a standard deck of cards, there are normally 52 cards, 12 of which are face cards. Jack, Queen, King of 4 different suits. And if you want to get into a fight about whether an ace is a face card, save yourself the energy, go find an ace, and find the face on it, and you will find out that you were wrong. So a king, a queen, and a jack in 4 different suits is 12 face cards. So the first way we're going to play this is 12 face cards and 12 not face cards. Now that's a weird way to set up a deck of cards, but I'm trying to demonstrate a point about how the mechanics work. So suppose I've got the jack, the queen, the king, and the 2, the 3, and the 4 of each suit. So if you think about that, there's 24 cards in this special deck. 12 of them are face cards, 12 of them are not face cards. So you're equally likely to be able to get a face card or not a face card. It's the same as saying I want to roll a 6-sided dice, and some of the numbers are odd, some of them are even. And it's about half and half either way. So if we were to actually play this game, the first time you deal a card, you either get a face or you don't. The second time you draw a card, you either get a face or you don't. Now, I'm going to have to draw a branch over here. So I maybe got a face, then a face, or a face, then not a face. I could have gone this way and had not a face, then a face, or not a face. So if I give you some arrows there to follow what's going on here. Draw number 1, draw number 2, and then draw number 3. So this is just like the tree diagram from the dice games, except it has one extra set of branches. So face, not face, face, not face, face, not face, face, not face. So I'm going to go through and I'm going to count up these results. So over here, if my first draw was a face, second was a face, and third was a face, that's 3 face cards. That's the big prize. That's the one everybody's hoping for. If I went this way, no face, no face, no face, that's 0 face cards. That's the one everyone's trying to avoid. And then all the rest of these are some combination of face cards. So if I just follow the branches and count the faces, none, none, 1. None, 1, none. So that's a total of 1 face on this branch. This would be 1, 2 faces. If I went this way, that's 1 face, 2 face, very exciting. And then the third one, you don't get it. So that's a total of 2. Face, no face, face is 2. Face, no face, no face is 1. So if I were to take a look at this, there are 4 different ways that this experiment could end up. I could get no faces. I could get 1 face card, 2 face cards, or 3 face cards. The next column, the probability, depends on how we're doing this. So the first way we're going to do it is, once you draw a card, put it back in the deck. And reshuffle. So if you do that, you pull this card out, the probability of it going that way is that there are 12 cards out of 24 that are face cards. So the probability of you ending up going that way is 12 out of 24. If you put that card back and reshuffle it, there are still 24 cards in the deck, and there are still 12 of them that are face cards. So the chance of you getting a second card that's a face card is still 12 out of 24. And then if you put that card back in the deck and reshuffle the deck, then there are still 12 face cards and there are still 24 cards in total. So your chance of getting there would be 12 out of 24. Now if you were to follow this all the way through, the probability of going this way is 12 out of 24. Probability of going here is 12 out of 24. Probability of going here is 12 out of 24. So the probability of doing this and this and this, if you remember from earlier in the unit, and implies multiplication on independent events. So pulling a face card now, if you put it back, has nothing to do with you pulling a face card on the next try. So those are independent. So the probability of getting a face, then a face, then a face ends up being 12 out of 24 times 12 out of 24 times 12 out of 24, which ends up being 12 times 12 times 12 is 1,728, and 24 times 24 times 24 is 13,824, and 1,728 divided by 13,824 is 0.125. Now, if you have solid fraction skills, you would have realized that 12 out of 24 is the same as 1 out of 2. And a half times a half times a half is an eighth, 1 out of 8, which happens to be this very decimal there. So it doesn't matter which way you calculated it, whether you took the full 12 out of 24, or if you knew to reduce it to 1 out of 2. It's up to you. It ends up with the same value anyway. Now, if I were to go down this particular pathway, the probability of getting not a face card is, again, 12 out of 24. And as long as I put that card back in the deck and reshuffle it, then for my next draw, there are still 12 non-face cards out of 24 cards in the deck. And as long as I put that card back in and reshuffle, there are still 12 non-face cards and 24 cards in the deck. So the probability of getting no face cards would be this one times this one times this one, which is identical to this option here, 12 out of 24, 12 out of 24, 12 out of 24, for a total of 0.125. Now, these other branches are a touch more complicated, just a touch. So if I were to follow them through, to get to this place here where I have 2 face cards, I would have to get not a face card, so that's 12 out of 24. And as long as I put that card back in and reshuffle the deck, to get to this branch, there are 12 face cards and 24 cards in the deck. This is familiar, right? This is happening again. And as long as I put this card back in the deck, there are 12 face cards out of 24. So I've ended up with this same fraction multiplied by itself 3 times. But if you look at this chart, this times this times this will end up at the end of this branch. So 0.125. It's also going to end up at the end of this branch. And it's also going to end up at the end of this branch. So, you could get 2 face cards by getting not, then face, or face, then not, then face, or face, then not. Now, you notice I'm using the word or to combine those 3 different probabilities. And earlier in the unit, that word or was prompting you to add the probabilities together. So there's a 12.5% chance of this one, a 12.5% chance of this one, and a 12.5% chance of that one. So 12.5 plus 12.5 plus 12.5 ends up being 0.375. for the one face card result, if we're always putting the card back in, there's always 12 face cards, and there's always 12 not face cards, and there's always 24 in the pile. So I'm still using this fraction over and over and over again. So to get to the end of this branch is also 0.125, as is this one, as is this one. But I could have one face card on this branch, or this branch, or this branch. 3 of them at 12.5% each is 0.375. So I'm going to clean this up a little bit, because I don't need to see the fractions anymore. I just need that decimal. And we're going to build the chart to work out the expectation value and see if this game is in the player's favor or the dealer's favor. So if I add into my column here the prize, if you get no face cards, you get no money. If you get one face card, you get $1. 2 face cards, you get $2. 3 face cards, you get $3. So if I were to take the prize and multiply it by the probability of winning that prize, 0 times 125 is nothing. $1 times 0.375 is $0.375. $0.375 times 2 should be 64, should be 75. Let's check that. 0.375 times 2 is 0.75. And 0.125 times 3 is 0.375. So if I were to add these all up, I'm going to have to budget 37.5 cents per game in order to pay this prize in case it comes up. I'm going to have to budget 75 cents per game to pay this prize in case it comes up. I'm going to have to budget 37.5 cents to pay for this prize in case it comes up per game. Altogether, once I add up my budgets, I have 0.375 plus 0.375 plus 0.75 ends up giving me $1.50. And the dealer is only charging me $1 to play, but they're expecting to pay out $1.50 worth of prizes each game. So this particular game, if I'm playing with only 12 face cards and only 12 not face cards, so that the odds are 50-50 of getting a face card, and I'm putting each card back into the pile and reshuffling so that the probabilities of each branch don't change, then this game is rigged towards the player. The player pays $1 to play and is expecting to get $1.50 back. So under this machinery, this game is going to end up moving money from the dealer to the player. So we're going to try this game again, but under different circumstances. I'm going to leave my 12 face cards in, but instead of limiting the not face cards to the 2, 3, and 4 of each suit, I'm going to use every card in a standard deck. That means that there are 40 not face cards and 12 face cards for a total of 52 cards in that deck. The tree diagram doesn't change. I flip a card, it's either a face or it's not. If it was a face card, when I flip my next one, the second one is either a face card or it's not. If I had a face card and I flip my third card, it is either a face card or it is not, and then the game is done. So you could either get a face and a face and a face, or a face and a face and a not, etc. That hasn't changed. What has changed is that this one is less likely to occur than this one. So we're going to operate this two different ways. One is, the first one, I'm going to keep this little caveat here, that once you draw a card, you put it back in the deck, and then you reshuffle, so that the probabilities of each branch are not changing as we proceed. So if I were to look at the first deal, only 12 out of 52 cards are face cards. But 40 out of 52 cards are not face cards. On to the next branch over here. Because I took that card, put it back in the deck, and reshuffled it, to travel on this branch, there are 12 ways out of 52 that I could get a second face card. And there are 40 out of 52 where I don't. On this branch, I have 12 out of 52 ways of getting a face card, and 40 out of 52 where I don't. So if I were to follow that branch out there and make myself a probability chart, I suppose I could fill the rest in here for you. To face would be 12 out of 52. To not face is 40 out of 52. To face is 12 out of 52. To not face is 40. To face is 12. To not face is 40. To face is 12. Not face is 40. Alright. So our outcomes remain the same. You could either get no face cards, one face card, two face cards, or three face cards. When I go to work out the probabilities, in order to get no face cards, that's only on this branch. It's the only one where that happens. For that to happen, I'd have to get a no face, which has a probability of 40 out of 52. Then I would have to get another no face, which has a probability of 40 out of 52. And then I would have to get a third no face, which is 40 out of 52. And if I do 40 times 40 times 40, I get 40 times 40 times 40 is 6,000, or 64,000, sorry. And 52 times 52 times 52 is 140,608. And 64,000 divided by 140,608, 608 is 0.4552 if I round. So that probability has increased. I think it was 12.5% under the original rules, and now it's almost half of the time you don't win a prize. So this is drastically changing which way this game is skewed. For my next outcome, one face card, that's on this branch, or this branch, or this branch. Do you notice that I'd have to do 12 out of 52 times 40 times 40, or 40 times 12 times 40, or 40 times 40 times 12? Doesn't matter which branch I go down, there are two 40s and one 12. So if I were to do that, 40 times 40 times 12, I'm just going to do it on this particular branch so you can see it. 40 out of 52 times 40 out of 52 times 12 out of 52 gives me 40 times 40 times 12 is 19,200 out of 52 times 52 times 52 is 140,608. And as a decimal, that is 140,608. 0.1365. All right. Now, to go down this branch, where I get 2 face cards, I'm going to have a 40 and a 12 and a 12. Or a 12, then a 40, then a 12, or a 12, a 12, and a 40. Notice that there are 2 12s and 1 40. So 2 12s and 1 40. 12 out of 52, and a 12 out of 52, and a 40 out of 52 ends up giving you 12 times 12 times 40 is 5,760 divided by 140,608 is 0.04096. So that's going to round to 0.041. And if I follow the path that gets me to 3 face cards, I have 12 times 12 times 12 out of 52. So 12 times 12 times 12 is 1,728 out of 140,608 is 0.1228, 0.01228, which will round to 0.123. That's a fun number. .0123. All right, I'm going to get rid of these because I don't need to see them. Now, as I write this up here, I have made a mistake on purpose to see if you catch it. So if you looked at these probabilities, I'm going to get these out of my face too, so that we can see each other. I have a 45% chance of this one, a 13% chance of that one, 4% of this, and a 1% of that. Now, 45 and 13 is 58, plus 4 would be 62, plus 1 would be 63. And there's a little error in there because I'm rounding, but 63% isn't even close to 100. And there aren't any other options. You either get no face cards, 1 face card, 2 face cards, or 3 face cards. So something is missing. And if you think about it, you look at the branches. This number here, 0.1365, that was for this branch. But that branch happens here, and it happens here, and it happens there with the same probability. So you have a 13% chance of this happening, or this happening, or that happening. You're supposed to take those and add them together. So 0.1365 plus 0.1365 plus 0.1365 gives you 0.4095. So I had forgotten to multiply this by my 3 branches, so I'm going to fix that. That's going to happen on this branch as well. 2 face cards showed up on this branch, and that branch. So I'm going to have to do 0.0410 plus 0.0410 plus 0.0410 and get 0.123. Well, that's fun. That's like this one. Except the decimal place is in a different spot. Now if I were to quick add those up, 0.4552 plus 0.4095 plus 0.123 plus 0.0123, I get 1 right on the head. So when you build one of these probability distributions, especially when it gets complicated with different branches having different probabilities, you should always check that all of your outcomes add up to 100% or 1.0 as a probability. All right. Now, you can see in this distribution that things have changed dramatically from last time. This used to be only 12.5%, and this used to be 12.5%. This one is 10 times less likely, and this one is almost 4 times as likely, and this is the one where the prizes didn't show up. So if I were to go through and finish this chart, $0 for no face cards, $1 for 1, 2 for 2, 3 for 3, and I were to work out the expectation, multiplying the probability times the prize, then I have to budget $0 for this one, $0.4095 for this one, 0.123 times $2 is 0.246, and 0.0123 times $3 gives me 0.0369. And if I add those all up, plus 0.2460 plus 0.4095, I end up with 0.6924. So I'm expecting to pay out 69.24 cents per game, but I'm collecting $1 per play, which means that this game under these circumstances, now that I've added in all the face cards, is now moving money towards the dealer instead of towards the player. So per game, $1 minus 0.6924 is 30.76 cents per game. And if you played this for an hour, and it took about 10 seconds per game, so 6 games per minute times 60 minutes in an hour is 360 games. So this times 360 is $110.74 per hour. It's not as profitable as the game that came before, but that's still pretty good as an hourly rate. So you see how one change in the mechanics of how the cards are dealt, or how many cards are in the deck, changes the outcome of how this game moves money. Now that shouldn't surprise you. I mean, if I made it harder, if I put more non-face cards in, I've made it harder to win. And if it's harder to win, then it should be less likely that the player is going to get the money. If you think about this game here, you win prizes on this probability, and this probability, and you only lose on this one. This is less than half the time. So if you were watching someone play this game, 1 out of every 2 people at least get their money back. So if you were watching this go, you would say to yourself, well, I have a 45% chance of losing, which means I have a 55% chance of winning. So that's maybe worth taking the risk. And even though that's true, right? Like this it's not a lie. Even though that's the way it works, that you are getting at least your money back half the time, the fact that you are losing sometimes is moving $110.74 per hour towards the dealer. For the final analysis on this particular game, Chase the Face, I'm going to leave the full deck, so 12 face cards, 40 not face cards. But I'm going to remove this caveat that once you draw a card, you put it back in the deck and reshuffle. Instead of doing that, once you draw your card, you're going to lay it face up on the table. So let's take a walk through about what happens there. Play your card. Face up on the table. So, if that's how we're going to play this game, when I go to play my first card, there are 12 out of 52 that are face cards. And there are only 40, there are 40 out of 52 that are not. So fine, let's assume you get a face card on the first one. So we're going that way down the chart. When I go to draw my second card, I've already pulled a face out of the deck, which means there are only 11 faces left. But I've also pulled a card out of the deck, which means there are only 51 cards left. So you see how placing your card face up on the table means it's no longer available on the next branch. In the same vein, if I got a face card on the first one, there are only 51 cards left in the deck, but there are still 40 that are not face cards. Now, something to keep in mind when you're doing these to try and fact check your work. Do you notice that 12 and 40 added to 52 because you're either a face or a not face and there are no other options? On this branch, 11 face cards and 40 not face cards adds up to the 51 cards that were left in the deck. So just keep that in mind to make sure your work is correct. If I continue down this chain, if I got a face card, that means there are only 10 left for my next and my third and final draw. But there are also only 50 cards left to choose from. If I got a face and a face, there are still 40 not face cards and only 50 in the deck. So you can watch the probabilities of this evolve as you go down the chain. You notice that as I go, because my face cards are being depleted on this branch, it's getting harder and harder to get my next face card. If I were to go down these branches, so I got a face card, then I got not a face card. From this point, one of the 12 face cards is gone. That leaves only 11 face cards left and 50 cards to choose from. One of the non-face cards is gone, leaving 39 non-face and 50 cards in total. Again, notice that 11 and 39 add up to the 50 cards in the deck. So going this way, if I got a non-face card on my first draw, then there are still 12 face cards in the deck, but only 51 cards left in total. Because I already got a non-face card, there are only 39 left out of 51 in total. On this branch, I got a non-face and a face, which means one of each is gone, leaving only 11 of the 50 cards being face cards and 39 of the non-face cards out of 50. Here, if I got a non and a non, then there are still 12 face cards out of 50 and only 38 out of 50 are not face. So it gets a little more complicated here as I try and build this chart. So my results well, they haven't changed. I either get no face card, 1 face card, 2 face cards, or 3 face cards. In order to get no face cards, this is the only branch that happens on, I would have to have no face card on the first time. That's 40 out of 52. And then I'd have to travel down this branch, which is only 39 out of 51. And then I would have to travel down this branch, which is 38 out of 50. So 40 times 39 times 38 times 39 times 40 times 39 times 38 is 59,280. And 52 times 51 times 50 is 132,600. And 59 to 80 divided by 132,600 is 0.4471 if I round. Now I think that this was 45% in the last example. So by taking your card and laying it on the table instead of replacing it in the deck, you've actually made it harder to lose, which is good. We want to win. If I were to do this one, the 1 card option, I would have to get to either here or here or here. Do you notice that on this branch I have 40, 39, and 12. On this branch I have 40, 39, and 12. On this branch I have 40, 39, and 12. So the probability of landing on any of those branches is going to be 40 out of 52 times 39 out of 51 times 12 out of 50. And it's going to happen 3 times. So I'm going to have to end up doing 3 times 40 out of 52 times 39 out of 51 times 12 out of 50. Now you might be saying, but they didn't happen in that order. Well, that's true. On this branch, it was 40 out of 52 times 39 out of 51 times 12 out of 50, which is exactly what I wrote. On this branch, it would be 40 out of 52, write that, it's right where your face is, Jared. 40 out of 52 times 12 out of 51 times 39 out of 50. Now the 12 is over the 51 and the 39 over the 50 instead of the other way around. But when you do multiplication and division, multiplying these fractions, you do the numerators multiplied together and the denominators multiplied together. So the top is going to be 40 times 12 times 39, which is 40 times 12 times 39, 18,720. And 52 times 51 times 50, I already have from up there, 132,600. Now if I did them in a different order, 40 times 39 times 12, when you multiply things in a different order, it doesn't change the answer, right? Like 2 times 5 is 10, and 5 times 2 is 10. Didn't matter what order you did them in. So this row here, at the end of this branch, and this branch, the probability of getting there is going to be 18,720 out of 132,660, but it happens 3 different ways, either here or here or here. So I'm going to have to count that 3 times. And if I do that times 3, I get 56,160 out of 132,600 for a total of 0.4235. I think on the last example that was only 40%, so I've borrowed some of my losing outcomes and popped them into this get your money back category. Just going to get rid of these so it's not cluttering it all up. My two face cards options, I'm going to have to end up at this branch or this branch or this branch, and if you notice in the sequence there's a 40, a 12, and an 11. A 40, a 12, a 40, and an 11. A 12, an 11, and a 40. Either way, I have those three numbers, 40, 12, and 11, out of 52, 51, and 50. And it happens on this branch, and this branch. So I'm going to have three branches, all calculated by doing a 40 times a 12 times an 11. So 40 times 12 times 11 is 5,280. Triple it, because there are three branches that end that way, is 15,840 out of the 132,600 different outcomes, and I get 0.1195 if I round. For my last row, the three face cards, the only way to get there is on this branch. This times this times this. So I would have 12 out of 52 times 11 out of 52 times 10 out of 52, which gives me 12 times 11 times 10 is 1,320 out of the 132,600 different ways this goes, and I get 0.00995. And if I round that, it will end up being 0.010. Now, as always, to double check to make sure I've done this correctly, because that was a whole mess of numbers, I'm going to add this probability and this probability and this probability and this probability, and because they're the only options available, it should add up to 1. So if I check that, 0.4471, that's this one, plus 0.4235 plus 0.1195 plus 0.01 gives me 1.0001, and that is 1 with a rounding error. So we've got it. That's the proper probabilities. So I'm just going to clear them out so I have some room to do my expectation value. That's 0.4471. This is 0.4235. This is 0.1195. And this is 0.0100. So to finish my expectation value, I'm going to add that prize column into the chart of $0, $1, $2, $3, and then the expectation value will be the probability times the prize. So for that first row, as always, it's $0. Second row will be 0.4235 $0.1195 times $2 is 23.9 cents. And 0.01 times $3 is 0.03. And if I were to add all those up, 0.03 plus 0.2390 plus 0.4235 is 0.6925. So if you play the game this way, where instead of putting the card back in the deck and reshuffling, instead you lay the cards out on the table, which is traditionally how card games are played, you have changed the probability and hence the expectation value. This time, you're going to have to budget 69.25 cents per game in order to pay these prizes. So that's still skewed towards the dealer. They are expecting to make 30.75 cents per game. And under the same assumptions, it takes about 10 seconds to play. That's 6 games per minute, and 60 minutes per hour is 360 games per hour. So they'd be able to make $110.70 each hour playing this particular game.